Bonjour. Welcome to Wahsa Distance Education Center's radio Zoom classes. This is MBF3C grade 11 college math, and I'm the teacher, Bronwyn Slate. If you'd like to participate live today, you can call the Wahsa studio at 1-800-465-7144 or 737-4017. You can listen on the radio at 91.9 FM and also on the television at Bell Express View channel 972. You are always welcome to join me live through the Zoom link, which is available both from me, your teacher, and also your DEC. Our classes are scheduled Monday through Thursday from 2 until 3 in the afternoon, and we are in our 8th week of our 9-week course. You definitely should know what to submit at this point, but a reminder that the support questions are not for marking, they are practice problems, and you decide which ones and how many to do. If you're understanding a concept, it's totally fine to skip questions and spend the time on things that you don't understand or you need more support with, more practice with. That's totally fine. If you need more practice problems, let me know and I'm happy to send you more questions. The answers are in the back of your booklet, so check your work to make sure that you're on the right track. The key questions, however, are the marked questions. They're the ones with the little key icon, and these ones please submit to me. Make sure you're doing all of them, as well as that you're showing all of your work, your steps, and your thinking so that I can truly understand what it is that you understand and can figure out how to support you if you need some help. How do you submit your work for marking? Well, there's 3 methods. The first is to scan your work and send it electronically. You can scan your completed work through a device. If you have an Apple device, you can use the Notes app. And if you have an Android device, you can use the Google Drive app. Both these apps are free and fairly straightforward to use. If you need some support to figure out how to use them, I have videos on my tech tutorials on my YouTube channel that help walk through each of these apps and how to use them. If you can only take pictures, if that is what makes the most sense for you, totally do that and send them. Scanning just makes the files a little bit easier to send and generally one file opposed to a whole bunch of pictures. Then you can send them to me through email to studentwork@nnec.owen.ca and CC it to bronwyn.slate@nnec.owen.ca. Or you can also send it to me through Facebook Messenger, where my name is B. Slate Wahsa. The second method is to drop your work off in Sioux Lookout. We have an outdoor mailbox at our 74 Front Street location. We are the bright red building next to the post office, and we have a small white mailbox next to our side entrance. The third method is to hand it into your DEC. Then your DEC can send your work through the Express or fax it to 807-737-1732 or toll-free fax to 1-800-463-7852. Students can also fax their work in if that's something that's convenient for you to do, though it's a really good idea to either call us or send us a message saying that you have sent your work through the fax, as sometimes it doesn't show up the way that we are expecting it. So just to check in to make sure that we have received it. If you'd like to connect with me through social media, both my Facebook and my YouTube channel are under the name B. Slate Wahsa. So you can friend me on Facebook or subscribe to my YouTube channel, and then you will get notifications every time I upload one of our radio Zoom classes. All of our radio Zoom classes are recorded and I upload them to YouTube shortly after broadcasting. Also on my YouTube channel, there are short videos that explain common errors and confusing concepts that might be useful for you if you are struggling with something that isn't actually a course concept, but is a foundational tool that you need. So that's a good place to go and check out if you're struggling with something. Math is a really visual subject, so I strongly encourage you to access the videos, either joining me live through Zoom, even if you don't want to ask me questions, that's fine, or watching the replays on YouTube. That is totally fine too. If neither of those ways work for you, let me know and I'm happy to send you a copy of the videos so that you get the full experience and really set yourself up for success. If you have any questions or concerns, please reach out and contact me. My email address is bronwyn.slate@nnec.owen.ca. My Facebook again is B. Slate Wahsa. Calling me at the office works at 807-737-1488, extension 2209. or calling toll free at 1-800-667-3703. My office hours are Monday through Friday, 9 a.m. till 3 p.m. Though I teach the last hour of my day, so that is not a great time to try to get a hold of me. So we are diving into lesson 19 today, which is theoretical probability. So our learning goals for this are that at the end of this lesson, you will be able to calculate the probability of something happening, and you understand the probability terminology, and you'll be able to represent probability in a variety of ways. You know you've met the learning goals because you could calculate the probability of a desired event. You can use probability terms accurately, and you are comfortable with probability represented in various forms. Answering the question, when will I use this in real life? Because this is what we all really care about. We are strengthening our ability to think critically. This is a transferable skill that is going to be in your life no matter if you are working in Tim Hortons or the grocery store or being a healthcare worker or in education or being a lawyer or an activist or a business person in the stock market. Any of these, any job, and even being a parent and having relationships with other people, all of them, you're going to need to think critically sometimes in your life. And so this is an incredibly important skill. And though probability might not show something up as something that you're using every day, being able to think critically about the things that are happening in your life every day is super important. Okay, but let's first activate your brain with some mental math. I don't believe in mad math minutes. They cause people stress and anxiety and don't teach any skills or work on strategies that make you comfortable with numbers. So instead, we work on developing strategies that do develop comfort and confidence with numbers, and that you focus on numbers that are friendly for you. Our question today is 424 plus 193, and we are using the strategy of breaking up by place value. So you generally, when people are learning how to add, they're told to stack them and start at the left and start at the right and work to the left, which is like backwards from how we read in English. And that is totally fine, that you can follow the steps of the algorithm and that works. But instead today we're going to look at the numbers and think of them as their wholes. So 424 is 400 plus 20 plus 4, and 193 is 100 plus 90 plus 3. And so we're breaking them into these place value parts so that we now are just thinking of what is 400 plus 100? Well, that's 500. And what is 20 plus 90? That's 110. And what is 4 plus 3 is 7. So breaking those parts off were fairly manageable chunks to add. And now we will add those 3 parts together. So 500 plus 110 is 600, and 10 plus 7 is 617. So 424 plus 193 is 617. Again, you can use this with decimals too, and any amount of digits. It's breaking it up. So you need to be comfortable to expand to break your numbers up into place value, but this can be a really useful tool for when you're adding awkward numbers. All right, mine's on. What do we need to know to set ourselves up for success today? I just wanted to do a quick review about decimals, fractions, and percentages, as they are different ways of showing the same number. So especially when we're talking about probability, often we interchange these. We'll say 50%, and we might write it down as 1/2 as a fraction, or 0.5 as a decimal, or 50%. And all of these things in my brain are the exact same thing. They're just different ways of looking at the same thing. Sometimes I like to explain this to students the same way that we have different names depending on the context. So in mainstream schools, often they expect me to go for me to be called Miss Slate. That's the name that mainstream schools want teachers to go by. I prefer to go by the name Bronwyn, which is where I go by most places, as most people just call me Bronwyn. My kiddo calls me Mama. So I am the same person, but depending on the situation, my name, I can get called different things. So the same way with this, decimals, fractions, percentages are the same thing. They're representing the same thing, but they're looking slightly different depending on the situation. Okay, so that's what we need to know as we go in, is that just keep coming back to that as depending on the numbers that we have. All right, what's new? What are we looking at? So talking about probability, where this shows up in the world around us is in lots of different places. So some places that we might use more often than others is the probability of precipitation or the temperature. So the weather report or the weather prediction forecast doesn't tell you exactly. You can't bank on it in terms of exactly what it's going to be. We're predicting it based on weather patterns and about historical patterns. And the chances are based of this happening based on this information. So this is all part of probability, is how all of that is described and discovered, is based on calculations that include probability, how likely things are going to happen. The stock markets also include, and also like gambling, how likely something is going to happen. So this image, I believe, is looking at like football stats in terms of how likely something's going to happen in the first quarter, second quarter, and third quarter. So that, and giving different values to that depending on how likely, more likely it's going to be a higher value, and less likely is going to be a lower value. Also, in terms of risk analysis, and this could be in the stock market, this also could be in healthcare. So insurance, these are places where they look at risk of something happening based on, again, personal previous history, or also demographic previous, like averages and chances of things happening. And that can all be calculated in terms of when the doctor says, well, this is the chances are that you're going to have this risk, if you're going to the surgery, this risk of these side effects. That's all probability, again, makes that happen. And then this final one is another one that we use fairly frequently in our day, is like when you look at Google Maps or some sort of GPS system that tells you how long it's going to take to get from one place to another place. That again is putting in, like, calculating probability of the traffic being this amount and this distance, speed included, things like that are all calculations that are happening in the background to tell you that it's going to take this long to get from this place to this place. So probability really shows up in a lot of really different ways in our lives. So let's do some vocabulary to make sure that we're all on the same page when we're talking about these concepts. This is on page 21 of your booklet. So first, what is probability? What are we even talking about? So this is the chance that a particular thing will occur, how likely something is going to happen. It measures in a ratio out of the total of possible outcomes. So you're comparing it to all of the possibilities. How likely is this one possibility going to happen? It ranges between 0, which is impossible, cannot happen, no chance of happening, to 1, which is certain, definitely going to happen. So between 0 and a half, it's not likely. At a half, it's equal chance likely. Between a half and 1, it's likely to happen. So yes, we'll look at as we go around. So then successful result is another thing that comes up. So this is what you are hoping to measure or achieve. So this is what you're looking for. This is what you're hoping to happen. But it doesn't have to be a positive outcome. So just because it's called a successful result, it doesn't have to be something that society might equate to be positive. So your situation is going to define what a successful result is. So if you are measuring the probability of calculators being broken in a shipment or eggs being broken in a shipment, then a successful event is going to be, you might define it as being a broken egg. Even though you probably don't want a broken egg, but that is what you're measuring. That's the probability that you're trying to figure out how likely is that our egg is going to be broken. Trials are the number of times an action is repeated to complete an experiment. So how many times you are measuring your information, doing an experiment over and over again. These are called trials. Sample space is the collection of all possible outcomes of an experiment. So like with my broken egg situation, either my sample space might include a totally cracked egg, a slightly cracked egg, and a not at all cracked egg. Those would be all my possible outcomes for my test. That would be my sample space. An outcome is the specific and possible result from a trial of the experiment. So it's what happens when we call an outcome, it's the possible things that could happen. So that's just the phrase that or the terminology that we use. And an event is the probability of a certain outcome. So the chances that a specific thing is going to happen is what you're measuring, is what the event is called. All right, so first we're going to look at experimental probability to just understand a little bit more about probability. So this is determined based on the results of an experiment. So an experiment is you actually doing something. And the probability of the experiment is defined by or calculated by this formula, which is P of A. So this is the probability of A happening is equal to the number of successful results divided by the total number of trials. So for example, if we're using a die, find the probability of rolling 3 in 10 rolls. So we have a dice, we're just rolling it. What is the chance of rolling a 3 if we roll it 10 times? So I'm going to take you to this is Mathigon, is a place that's got some great manipulatives, and I'll link this in our show notes so you could try it out if you want to. So I'm trying to roll a 3. So I have a dice, I'm going to roll it. And it rolled a 5. So that I have 10. So I got, my first roll was a 5. I'm just putting a little marker there. My second roll was a 3. That's what I was looking for. My third roll was a 4. This is just, I'm just like making a tick, like it's like a tally that I'm using. I got another 5. And a 2. So you can do this with physical dice. Here, if you don't have access to a physical dice, then you can use this virtual option. So we can see it in our experiment, we are getting a lot of 5s. Ooh, we finally got a 1. And our last roll, we got a 6. So here, if we look at this, our experiment probability, we rolled it 10 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rolls. And how many times did a 3 happen? Only once. So the experimental probability of rolling a 3 is 1 out of 10, because we did the experiment, we rolled it 10 times, so that's our total. And how many times did our successful outcome happen? Our successful outcome was rolling a 3. It only happened once. So the number of, so how we would write that down is the probability of 3 is equal to number of successful results. We got it. We only rolled a 3 once. Total number of trials was 10. So 1 out of 10 was the probability of rolling a 3 in terms of this experiment that we just did. So then theoretical probability on page 21 of your booklet is when all the outcomes of an experiment are equally likely. So this is, in life, we want to be able to make predictions and analyze information without having to do an experiment. So experimental probability means that we're actually doing it, but only rolling a dice 10 times doesn't give us very accurate information about how likely it is to roll a 3. Because you have to do it so much. You have to do it like 1,000,000 times in order to get more realistic results. So with theoretical probability, we're now looking at how likely something's going to happen compared to all the outcomes theoretically using our logical brains. So how this works is that our probability of event A equals the number of desired outcomes divided by the total number of possible outcomes. So this is very similar. Experimental, it was the successful outcomes divided by the total number of trials, whereas theoretical probability is the number of desired outcomes divided by the total number of possible outcomes. So for this, what is a theoretical probability of rolling a 3 on a standard die, which is what we just did. Experimentally, we found it was 1 out of 10. But with theoretically, to get a 3, the number of desired outcomes is 1. There's only 1 3 on a die, and the total number of possible outcomes is 6. Right? There are 6 different options that we could get. So getting a 3 is only 1 out of 6 ways. So we would expect, generally, when doing that experiment, we would expect that 1 out of 6 times we would get a 3. And that's not what we got. We got 1 out of 10 times we got a 3. And if we have been doing this in a classroom where we had a whole bunch of students doing different things, each of those experiments would be different. You would have all gotten different results. But if we would have combined all that information and figured out, in general, it was more likely we're going to get pretty close to 1 over 6 as the probability of rolling a 3 with a dice. Okay, so common examples that theoretical probability comes up, things that we often talk about in questions or when we're thinking about this, is rolling a standard dice. So that has 6 sides, it's a little cube. We count the pips is what they're called. So they could be dice that have these little dots on them and that each represent 1. So 1 dot is equal to 1. This one has 2 dots. This one has 3 dots, 4 dots, 5 dots, and 6 dots. Or they also could have numbers. That could also be something that you might be rolling. That totally works too. For all of these, the number of desired outcomes depends on the situation that you're talking about, and the total number of possible outcomes is going to be 6. You always have 6 sides. So here, the probability of rolling a 5 is 1 out of 6. The probability of rolling an even number, so this is slightly different because there are 2, 4, and 6 are all even numbers. So there's 3 desired outcomes. Any of those 3 numbers could be a successful event. So there's 3 out of 6, which is equal to 1 out of 2, which is equal to half probability of 50%. Another common example is flipping a coin. So there are 2 sides to the coin. Generally a heads and a tails is what we call them. And here I have an example of a toonie. So heads being the side with the queen's head on it, and tails being the side that does not have the queen's head on it, has the animal or boat or whatever, depending on the coin that you have. Heads is the side with the person. So the number of desired outcomes, so the probability of this when you're using a coin is the probability of heads is 1 out of 2. You have 1 desired outcome out of a total possible 2 outcomes. So then if we extend this, what is the probability of flipping 2 tails in a row? And that's when things start to get a little bit tricky. And so it's not as easy to just say that it's 2 out of 4, because that's the same as 1 out of 2. But 2 out of 2 would mean that it always happens, which isn't true either. So we have to look at this a little bit more carefully in terms of how to figure that out. Drawing a card is another example of probability that is often. So from a standard deck of cards has 52 cards and does not have any jokers. These are all examples that do show up in your booklet, I believe. There are 4 suits, just in case you are not familiar with a standard deck of cards. There are diamonds, clubs, hearts, and spades. There are 13 cards per suit. So 1 through 10. 1 is also called an ace. It has an A on it. It has 1. And then Jack, Queen, King. So there's 13 for each suit, 13 cards. And there's also 2 colors. Diamonds and hearts are red. Spades and clubs are black. So to look at the probability if you're dealing with cards, the probability of choosing an 8 out of the deck of cards, well, there's 4 8s in the whole deck, which is 50 out of 52 cards. So the desired outcome is 4. The total number of possible outcomes is 52, and that can simplify to 1 out of 13. The probability of a heart, well, there are 13 hearts in the deck, so 13 over 52, your total possible outcomes. So that simplifies to 1 out of 4. Chances of picking a heart out of a deck is 1 out of 4, where the chances of picking a 8 out of a deck is 1 out of 13. You're not as likely to pick 8 as you are to pick a heart. And then if you wanted to simplify even, or to specify it even more, the chances of picking the king of spades, probability of that is 1 out of 52, because there's only 1 king of spades in a deck of hearts. Sorry, a deck of cards. There's only 1, so it's 1 out of 52. And then also a spinner is another common example. So it really depends on the number of divisions. So it's not something that is standardized, because a spinner isn't standardized. So often spinners can have quarters. So if it has quarters, then the total possible events are 4. So the probability of getting a red is 1 out of 4. This second spinner I have, the total number of sections are 5. So the total possible outcomes are 5 to get a green or purple. So they have 2 outcomes that are possible. So 2 out of 5. Or here I have a spinner that has 3 sections. So the probability of getting a blue is 0, because there's no blue section. So it's 0 out of 3, because no matter what I spin it, I'm not going to get blue. So the spinners really depends on how many sections you have on the spinner. Okay, so those are sort of how we generally think about probability when we're starting off. Our next tool that we're going to talk about are tree diagrams. So if we think back to when we're talking about tossing a coin, we talked about, we wanted to know what was the probability of flipping 2 heads in a row. So we're going to use a tree diagram to show what our possible outcomes could be. So first, there are 2 branches, 1 for heads and 1 for tails. So we are flipping a coin, and we have 2 options that could happen. Either it could turn into a heads, or it could land on a tail. The probability of each branch is written on the branch of our tree diagram. So the probability of the heads is 1/2, right? 1 out of 2 outcomes, which is 0.5 or 50%. And the probability of tails is 0.5, it's also 50%. Then the outcome is written at the end of the branch. So we have this line. You don't have to, if you're writing this down, you're not going to write all this probability, outcome, and branch. Those parts you're not going to write. This is just us learning. You're going to draw this green line for the branches, and then you're going to write the probability amount and the outcomes amount. Chances are pretty good you're going to actually write the outcome amount first, like title first, and then write the probability, but you could do whatever works for you. Okay, so let's look at extending this tree diagram. That was just a quick one for flipping a coin once. So now let's see what it means if we flip it twice. So on our first flip, we have this tree diagram, and this is how you would draw it, is that you draw two arrows, you have two outcomes. One, you flip it, either it's going to be head or it's going to be a tail. And the chances of that happening, because we have a standard non-weighted coin, this is not a trick coin, it's going to be 50-50 chance of either of those things happening. Then we do a second flip, and so now we say, okay, well, the first flip was heads. Then our second flip, it could be heads or it could be tails. So after heads, after our first flip, now we have a branch going from heads or tails. Or if our first flip ends up being tails, we still have the option of being either heads or tails if we flip the coin again. So now you can see our branches have extended out more. We have more branches now, but our probability of heads happening after we flipped heads is still 50%. The probability of tails happening after we flipped heads is still 50%. The probabilities of that coin flip on the second flip doesn't change, even though we flipped the coin before. That has no, they're independent events is what we call them. They don't have any impact on the other one. Okay, so then how does that help us figure out anything? So now we can list off our outcomes. So we flipped it once, we got head, we flipped it twice, we got head, so we got head, head. Then our next option was we flipped it once, we got a head, we flipped it second time, we got a tail, so it was head, tail. Then we flipped it once, we got tail, flipped it the second time, we got head, so we have tail, head. And then a third time or a fourth time we flipped it, we got tails, and then we flipped it again, we got tails, so we have tail, tail. So here is a list of all of our possible outcomes that we could, flipping a coin twice, these are all the possible results we could have gotten. So to figure out the probability of flipping two tails, so we want a desired outcome of two tails. So there is one way to get two tails out of 4 possible outcomes. So this is our only way, is to flip a tail once and a flip a tail twice out of all of the 4 different options that we do get. So the probability of getting tails, tails is equal to 1 out of 4, because there's only one way to get it out of 4 possible outcomes. So if we ask another question, what's the probability of flipping one head and one tail? Doesn't matter which one comes first. Well, we have 2 ways that we get one head and one tail. We can either do head first and then tail, or tail first and then head. But we're still out of 4 possible outcomes. So the probability of flipping a head and a tail is 2 out of 4, which is 1/2. So it's more likely that you're going to flip a head and a tail than that you're going to flip 2 tails. Okay, so that now how do we actually do some calculations with probabilities? So Alice is choosing a drink and a snack. She has 3 drink options: pop, juice, and water. She has 4 snacks to choose from: fruit, popcorn, cheese, and crackers, and a donut. Alice likes all of her options equally in any combination, so she doesn't have a favorite. What is the probability that she will have juice and cheese and crackers? So how we're going to do this is that we're going to start with a tree diagram. Her first thing we're going to choose is a drink. She has 3 options. She could choose pop, juice, or water. Great. Okay. Each of these things are as likely to happen. So each of them are a desired event is 1 out of 3. The probability of each of them happening is 1 out of 3, because there's one way to get pop is to choose the pop out of 3 possible ways. So the probability of each of these is 1 out of 3, because it says that she likes them all equally. Then our next option is to choose a snack. So she has fruit, popcorn, cheese, and crackers. If she chooses pop, she can still choose fruit, popcorn, cheese, and crackers, or a donut. If she chooses, and each of those can happen equally as likely, right? So there's 4 options. So 25%, 0.25, or 1/4, remember these are all the same thing, just different ways to write them, is equally likely to happen. If you were to choose juice, it's the same thing again: fruit, popcorn, cheese, and crackers, and donut, each of them equally likely to happen, so 25% chance of happening. Or water, fruit, popcorn, cheese, and crackers, donut, equally likely to happen. So you can see why we call this a tree diagram, is because we're starting to branch out more and more and more. So if we are wondering what is the likeliness of juice and cheese and crackers, well, we can see there's only one way that she could get that. Only if she chooses juice and cheese and crackers. So there's only one possible outcome out of all of our outcomes. So how we can figure that out is the probability of juice happening and the probability of cheese and crackers happening. So the probability of juice is 1/3 times the probability of cheese and crackers, which is 1/4. Multiply those together. You can either do them as fractions or you can use them as decimals. Either way is fine. And you get 0.08333 or 1/12, depending on if you do fractions or decimals. So that's the chances of her having juice and cheese and crackers is 1/12 or 0.0833 or 8%. All again, the same thing. Okay, another example of how we can calculate probabilities. Frances rolls a 12-sided die 4 times. What is the probability of her getting an even number for all 4 times? So here is, you can sort of see down here an example of a 12-sided die. We can only see 6 sides. We can only see half of it, but these die exist where you can have more than just 6 numbers. So we're wondering what the probability of rolling a die even 4 times. So we have to remember we have to do our desired outcomes divided by our total number of possible outcomes. So we're hoping that we're going to get even 4 times. So we're wondering what the probability of it even times the probability of it even times the probability of it even times the probability of it even. That's what we're wondering because we want all of them to happen. So we have to multiply our probabilities together. So there are 6 even numbers on a dice, on a 12-sided dice, because it goes from 1 to 12. There are 6 even numbers. So each of those are going to be 6 over 12 times 6 over 12 times 6 over 12 times 6 over 12, which is equal to 1,296 divided by 20,736. So that seems like a big number, which is equal to 1/16. You also could do this as decimals. So you could do 0.5 times 0.5 times 0.5 times 0.5 because 6 out of 12 is a half. So you could do decimals or you could do a half times a half times a half times a half. I don't know if that was 4 as a fraction, and you will still get, as you do as decimal, you'll go 0.0625, which is equal to 1/16. So you'll get them the same way, no matter what tool you use, depending on what is best for you is fine. All right, now you can do the practice problems, the support questions on page 22 to 23, questions 1 through 6. All right, we have a little bit time to do some practice problems, so let's do that. A pet store has 10 cats, 12 dogs, and 3 turtles. If Haley randomly selects a pet to take home, find the theoretical probability of getting a cat. So theoretical probability, we're not actually going to go and pick out cats. We're not going to actually do this as an experiment. So the chances of getting, the probability of getting a cat is equal to the total number of successful outcomes, desired outcomes. So there's 10 cats she could choose from out of the total possible outcomes. Well, how many animals are there in total? 10 plus 12 is 22, plus 3 is 25. So there's a total of 25 animals. So the probability of getting a cat, picking cat, is 10 out of 25. We like it best to simplify this as much as we can in order to just make it more manageable numbers. So 10 over 25 can simplify. Well, both 10 and 25 are divisible by 5. So if we divide 10 by 5, we get 2. And if we divide 25 by 5, we get 5. So the probability is 2 out of 5. The probability of getting a turtle, part B, is equal to, well, there's 3 turtles out of 25. Can I simplify 3 out of 25? No, they both are not divisible by the same number. So that we can't do that. the probability for C is a dog or a turtle. So this is key to think about, is that we're not looking for a dog and a turtle. It's a dog or a turtle, because this is going to make a difference. So for probability of a dog and a turtle, how many options are either of those going to happen? Well, we have 12 dogs and 3 turtles. So that means we have 15 options out of 25. So you just need to think about what are the, either getting a turtle or a dog would be seen as successful. So that's why we just can add them together, opposed to if you were picking a dog and a turtle, then it would be, the chances would be different. So 15 over 25 simplifies to be 3 over 5, because they're both divisible by 5 again. And those are the probabilities. All right, number 2, using a standard deck of cards, calculate the probability for the following situations based on an experiment of drawing one card from a well-shuffled deck. So what is the probability of drawing a red card from the deck? So probability of red. Well, remember there are 2 suits that are red, diamonds and hearts. And so if there's 13 cards of each, 13 cards of diamonds, 13 cards of hearts, then there's 26 cards in a deck of cards that is red out of 52 cards, which is our total number of cards. 26 and 52, well, we know that half the cards are red because there's 4 suits. So 1 out of 2 is what the probability reduces to. You could do 26 divided by 52, and you would get 0.5, or you could reduce them, divide them both by 26 and figure out that it's 1/2. However works for you. Reducing it to 1/2 means it makes it a little bit more sense to me. Looking at 26 over 52, my brain might not click in that that's a half, but looking at half, 1 over 2, I know that that's a half. What is the probability of drawing a heart card from the deck? So the probability of drawing a heart is equal to, well, there are 13 hearts from a deck. So that is 13 out of 52, which reduces to 1 out of 4. What is the probability of drawing an even numbered card, 2, 4, 6, 8, 10 of any suit from the deck? So not looking at face cards, but the probability of an even, because face cards are not even or odd. So there's 2, 4, 6, 8, 10. So that's 5 in each of the 4 suits. So that means that there's 20 even cards in total out of 52. So here, this one, I don't know off the top of my head of how to simplify it. I'm going to say, okay, well, I can see that they're both, I can cut them both in half because they're both even. So 10 over 26. And I can see, well, they're still both even. So I can do that again, which is going to be 5 over 13, which makes sense because there's 5 in each suit and there's 13 cards in each suit. What is the probability of drawing a face card from the deck? So the probability of a face card, well, there's 3 face cards per suit, Jack, Queen, King. There's 4 suits, so 3 times 4 is 12 out of 52. So that is going to, again, I can do it in steps. 6 divided by is equal to 6 over 26, which is equal to 3 over 13. Well, that's the probability of getting face card. Number 3, I want ice cream. The ice cream shop has the following choices: a cup or a cone, vanilla or chocolate, and sprinkles, nuts, or berries. Draw a tree diagram to show all the options. So you can start off in any order. You don't have to start off in the same order that I do. You could start with choosing sprinkles, nuts, or berries first, and then figure out if you want chocolate or vanilla, and then figure out if you want a cone or a cup. It doesn't matter. You're going to get to the same result no matter how you draw your tree diagram. You will note that drawing tree diagrams, you end up taking up an awkward amount of space. So starting off with a wide branch at the beginning is a good idea. So we have either the choice of a cup or a cone, and they are equally likely because we haven't said anything else. So I'm going to just write a half for each of those. And then after I choose a cup or a cone, I can choose vanilla. I'm just going to put V for vanilla or C for chocolate. After a cone, I could choose vanilla or chocolate. Again, chances of each of these happening is 1/2. There's only 2 options, so it's 1 out of 2. Then I could have sprinkles. I'm just going to put S. Nuts, I'm going to put N, or berries, B. And this is where you can see that it starts to get squished, because chocolate, I can do sprinkles, nuts, or berries. It does not need to be beautiful. Vanilla, cone and vanilla, sprinkles, nuts, and berries. And cone and chocolate, sprinkles, nuts, and berries. So that is a tree. Oh, and sorry, the chances of choosing sprinkles, nuts, or berries is 1 out of 3 for each of these, because there's 1 out of 3, one desired event out of the chances of 3 different options. So again, giving yourself lots of space can be really helpful, and being patient with yourself is that it might not be as beautiful as you initially thought it was going to be. Okay, how many different combinations are there? So we look to see there are a total of, I'm going to change my, I'm going to use a highlighter or a laser. Does this let me be laser? Yes. Okay. So going from a cup to vanilla to sprinkles is 1. Cup vanilla nuts is 2. Cup vanilla berries is 3. Cup chocolate sprinkles is 4. Cup chocolate nuts is 5. Cup chocolate berries is 6. Cone vanilla sprinkles is 7. Cone vanilla nuts is 8. Cone vanilla berries is 9. Cone chocolate sprinkles is 10. Cone chocolate nuts is 11. Cone chocolate berries is 12. So there are 12 different combinations. And you can, after doing this enough times, you'll notice that it's always the last branch of your tree always has all of the combinations. How many combinations would there be if the ice cream added another flavor? So if we had 2 options for a cup or a cone, and then we had 3 options for a chocolate, vanilla, or another kind of ice cream, and then 3 options for a topping. So you're going to multiply all these 3 together to figure it out. You could redraw your tree diagram, or you can see that 2 times 3 is 6 times 3 is 18. So there's going to be 18 combinations in total if we had another flavor of ice cream. How many combinations can Jane get with vanilla ice cream? So this is now you're looking at your tree diagram and trying to figure it out. So we have 3 options for vanilla and a cup, and 3 options for vanilla and a cone. So that means that there are 6 options if you just want if vanilla is the most important. How many combinations can Jane get if the ice cream shop runs out of nuts? So there were 4 with nuts. So if there's 12 in total, but 4 are taken away because there's no nuts, that means that now there's only 8 options. And how many combinations can she get with chocolate and strawberries? So chocolate and berries. So she can get chocolate and berries in a cup or chocolate and berries in a cone. So there's only 2 options. So these would be your desired amount. So we're not trying to find the probability right now. Right now, we're just seeing the desired options or successes. Okay, and those are the different types of questions you could be asked. So let's go over everything we've learned today. So we've been looking at lesson 9, which is theoretical probability. So remembering the terminology is really important, as I've used all of these terms a lot today. So making sure you understand those means that you know what I'm talking about. So probability, successful result, trials, sample space, outcome, and event are all words that I've used. Remembering that theoretical probability is equal to the number of desired outcomes divided by the total number of possible outcomes. Remember, desire doesn't always mean that it's a positive or something that's going to make you happy. It's just what you're looking for. Then we looked at tree diagrams, which display all events by using one branch for each possible outcome, including the probability. And then we looked at calculating probabilities where we determine the multiple events and multiply the probabilities of each event. So tree diagrams can be really useful. You don't have to use them just when I ask them to. If visualizing it helps you, then totally use tree diagrams to help you use the tools that you've got. Okay, so our success criteria, hopefully you are feeling that you can calculate the probability of a desired event, that you can use probability terms accurately, and you are comfortable with probability represented in various forms. And so in the tree diagram, and also with a half, the decimals, and the percentages, that's all good to be comfortable with that. All right, so that is our lesson today. If you have any questions, as always, please reach out and connect with me. Call me at the office at 807-737-1488, extension 2209, or toll free 1-800-667-3703. Send me an email at bronwyn.slate, and that's spelled BRONWYN.SLATE@nnec.on.ca. Connect with me through Facebook, where my name is B-Slate Wahsa. And also check out my YouTube channel that has all of our lessons on it. The channel is called B-Slate Wahsa, and there's a playlist under MBF3C, which is our course code. Next week, we will be reviewing all of the course material to set you up for success for your culminating activity. Thank you so much for joining me today. Miigwech.